Hey everybody, welcome to Mammoth Interactive's YouTube channel. First of all, I want to thank you for watching this video. And remember that this channel doesn't do Patreon. Instead, we sell our digital courses down below. And every single dollar that we get from the products you buy below goes into making more content. The best way to help out this channel and Mammoth Interactive is to subscribe to Mammoth Interactive's huge library of content. Get thousands of hours and hundreds of courses for a low price down below. We have a monthly option and a yearly option. Thanks for listening, and I'll see you in the video.
Hello everyone, and welcome back to our course. In this lecture, we are going to get started in Google Colab by loading in our dataset. So this is the dataset we're going to use, the CUHK Face Sketch database. And you can find it at this link. Of course, all the source files will be included for you at the end of this section. And also, in the previous lecture, I included for you the actual data set that we're going to use because I have downloaded it ahead of time for you from this website link. And I also did a bit of renaming and pre-processing as well, because the original data set is a bunch of photographs and corresponding sketches, and you can find training faces, sketches, and photos, as well as testing faces, sketches, and photos. This is what I downloaded and then I renamed for us and also unzipped. Okay, so this is the data set that we're going to use. There are other ones as well that you could play around with, and feel free to after this course. Okay, make sure that you have gone into the previous lecture and downloaded that source file that I've included for you. So it is called a dataset folder, and it has a test folder and a train folder. The test folder contains subfolders test photo and test sketch. These will be our images for testing. And you can see we have photographs of people as well as sketches in test photo and test sketch respectively. Then as well, we have the same in train. We have photos and we also have sketches. All right, so go ahead and download that data set, this folder that I've included for you, and upload it to your Google Drive, because we're going to be building our project in Google Colab, and we can actually just get folders directly from Google Drive. If you're not using Google Colab, if you're using a different code editor, perhaps on your computer that is offline, then you won't have to upload your data set to Google Drive. You can just save it somewhere on your computer. Okay, great. So once you have uploaded the two folders, train and test, from the dataset folder I provided, then we're now going to grab those folders and access them here in Google Colab. So in order to access Google Drive via Google Colab, we're going to first import from Google Colab the Drive module to access Google Drive. Then we're going to call drive.mount, and we're going to mount /content/G drive. So this means we can access our Google Drive at this root path. Okay, and then after this, we can create variables to store all of our 4 subfolders. We have train photo, test photo, train sketch, and test sketch. So let's start by making a variable that we will call our path to train photos. And the path is going to be /content/G drive /my drive /train photo. So make sure you use this exact path, because this means we're inside of my drive on Google Drive, and we're inside of the train subfolder, and we're inside of train photo. If you also included the dataset folder as a whole, then you'll have to include that before train. But in my case, I just uploaded train and test directly. Okay, so we have a path to our train photos. Next, let's make a path to test photos. And for that, you're going to access /content/G drive/my drive/test/test photo. Then we're also going to need a path to our training sketches and our testing sketches. So let's make path to train sketches, and that path is going to be /content/G drive/my drive/test/ or rather /train still /train/train sketch. So these are the folders that we have inside of the train folder. And then one more path, we need a path to test sketches. And that path is going to be /content/G drive/my drive/test/test sketch. Okay, great. And these are the 4 folders that we have. Next, let's grab the actual content in these directories, because each of these are folders. They're not images, but we need to get the images from the folders. So I'm going to start by making a variable I will call my photos. And these are going to be our train photos. So we could just call it train photos as well. And we're going to create an array of photos by taking path to train photos and adding I for every I in os.list directory of our path to train photos. So what we're doing here is we are turning our path into a list directory. So a directory is just a folder that contains items. And then for every item in that directory, for every item in that list, we are going to create an element in the array of train photos. Now, in order to access os.list directory or list dir, we do have to import the os module in order to have access to that function. So I am going to import os. And it's already pre-installed. We just have to import it thanks to Google Colab. All right, and next we have to do the exact same for all of our other subfolders. So I'm going to next make my train sketches. So my training sketches. And I'm going to create an array again. This time I'm using the path to train sketches. And I'm adding I for every I in an os.list directory of the path to train sketches. That will give us an array of images of the sketches for training. Then after this, let's create the testing data set. So I'm going to create test photos, this variable. And again, I'm going to create an array. I have to pass in here path to test photos plus I for every I in an os.list directory of path to test photos. And then finally, we have one more. We have our last sub data set, and that is test sketches. So I'm going to create an array using path to test sketches plus I for every I in an os.list directory of path to test sketches. Great, and just like that, we will have an array of images for all of our 4 subfolders. We can also combine all of the 2 together for training and testing, or optionally we can combine all of the photos with all of the sketches. So in my case, I'm going to add the photos together and the sketches together so I have them all in one. All you have to do to add 2 arrays together is you just have to use the plus operator. So I'm going to create photos by taking my train photos and adding my test photos. Then I'm going to also create sketches by taking train sketches and adding test sketches. Okay, so we can either work with them individually or we can add them like we just did. Awesome, and that is all we need in order to make sure that we load in our data set. So now when you run this file, you'll first have to authorize Google Drive. So just give it a moment and you will see here, you'll get this message, go to this URL in your browser and enter your authorization code. So you have to authorize Google Colab to access your Google Drive. So you just have to choose the account that is the same as your Google Colab account and then allow it to access Google Colab. So give it permissions and then copy the authorization code right here. So I'm going to do that. Then once you paste in your Google Drive authorization code, you'll get this message mounted at /content/G drive. That is the message you should get if you have successfully been able to connect your Google Colab to Google Drive. Okay, awesome. And just like that, we've built out one code cell of the project. All right, now that we have loaded in our data set, we can get on to our next step, which is going to be to process this data set. Data set pre-processing is a large portion of the machine learning workflow. It's an important step because we have to actually prepare this data for our neural network. It's not ready as is. So join me in the next lecture where we will process our data set. Hello everyone and welcome back to our course. In the previous lecture, we loaded our data set, and in this lecture, we are going to process the data. All right, so I'm going to create a new code cell for this because if we do everything in one code cell, then every time we run the code cell, we'll have to enter our authorization code again, and that gets a little tedious. So I'm going to make a new code cell instead and just run that code cell separately. And all of the code that's been previously run will still have been saved in this instance of the Collab. All right, and let's get started. We are going to begin by looping through every index in our range of all of the photos that we have. So we're going to go through all of the photos. And we are going to start by loading in the image at the path. And we have to do that for the photos and also for the sketches. So let's begin with the sketches. Okay, we'll make a path to the sketches. We'll call this our sketch path. And we are going to get our sketches at the current index. That will give us the path to one sketch image. And we can even print that out. We can print out sketch path, and you will see if I run this code cell, I'll see the paths to all of my sketches. And you should have something that looks exactly like this. If you put your folders into your Google Drive, inside of a test folder, inside of test sketch, and then the actual images themselves. Okay, and we can see all of those there. And we can see we have not just training sketches, but also testing sketches because we added our two arrays. Okay, great. So we do have the path to the sketch. Next, let's load in an image at that exact path. So we're going to use image.load_image and pass in the sketch path. Now you may be wondering, what is image.loadImage? Well, this image module, it comes from Keras. So at the top of our file here, let's import Keras. Keras is a library that is very commonly used. It comes from TensorFlow. And it has a lot of helper modules and classes for building neural networks and, in general, machine learning. All right, so from Keras, we want to access its sub-module pre-processing and import image. So we're going into the pre-processing sub-library and importing the image module here. This will allow us access to a whole range of functions specifically for pre-processing data. For example, the load image function. This comes from Keras. Make sure you spell it exactly like this, load image. And it is going to allow you to load an image from a path, and it's going to return a image type. So it will return a PIL image, a Python imaging library image. So we pass in the path here, and also we can pass in a target size as well as other optional arguments. The target size is the size I want my image to be. I'm going to pass here 128 by 128 by 3. So this means the width and height will be 128. And 3 is the number of color values. Because my images are not grayscale, they actually have colors, I have 3 as the color value because I have red, green, and blue as my 3 color values. All right, so this is going to load in the image at this current path. And we can store this as our, let's see, we can call this our loaded sketch. Okay, then we can do exactly the same to load in a photograph. So I am going to make a photo path variable here, and I am going to grab my photos, which I created in the previous code cell, and I'm going to grab photos at the current index. Then I could call print photo path to verify that indeed I do have a photo path. Now just make sure that you only have images inside of these 2 folders because we're looping through all of the contents. So make sure that you don't have any other files, because sometimes when you upload folders to Google Drive, you can accidentally upload other files, like even a path file, like to destore. And make sure you only have images. Otherwise, you will get an error thrown. And if you do have any other content in here accidentally, just remove it from that folder on Google Drive or on the folder on your computer if you're not using Google Drive. And make sure to remove it, and then just run the code cells again. And you may even have to reset the runtime to clear all the variables, because sometimes even if you run a cell a second time, it can still not change the effect because the variable was already saved. So you may have to go to factory reset runtime if you want to rerun the whole project again. So just make sure you only have JPEGs here. Then, after we have gotten the path to all of our photos, we are then going to load it in again. So I'm going to call image.load_image again. This time the path is the photo path. And the target size is going to be the same, 128 pixels by 128 pixels by 3 color values. Okay, great. And here we go. We can see all of our images here with all their names. And I don't have any other files in here except for JPEGs, which means I won't have any errors. Great. Okay. Next, now that I have loaded in my sketches and my photos as well, I can move on to my next step. So what I'm going to do is I'm going to make arrays. And I'm going to convert my images into arrays. So let's call loaded sketch again, and let's use Keras image, that pre-processing module, and let's use another function known as image_to_array. So we want to convert our images, which are just Python imaging library image types, and we want to convert them into arrays because machine learning neural networks, they can't work with images like JPEGs. You have to convert them into something that can be understood by math, which is an array. So we are going to call image.image_to_array, and we're going to convert our loaded sketch into an array, and then we're just going to resave the variable. Then we can do the exact same for our photos. So we're going to take our, our loaded photos, which we haven't saved yet. Let's save it as loaded photo. So we are going to take our loaded photo and override it. So we'll change its value. And we are going to use image.image_to_array again to convert the loaded photo from that JPEG into a array type instead. Okay, then let's create an empty array and append our loaded sketch and loaded photo to those arrays. So just outside of the for loop, I'm going to have an array to store all of my image arrays. So I'm going to have a multi-dimensional array. So I'm going to make an array here that I will call my sketches, or let's see, they should be arrays though. So I will call these sketches array. And it's going to initially be an empty array. Then I'll make photos array, and again, initially it will be an empty array. And then for every index, we are going to take that sketch and add it to the sketches array, and take that photo and add it to the photos array. So in the end, we'll have our two arrays which contain images represented as arrays. So to add each array into sketches array, what we will do is call sketches array, and we're going to use the append function to append the loaded sketch. All right, and you can actually just separate this into two halves. First, we're going to do all the sketches work, and then we'll do all of the photo work. Just make sure when you add or append the loaded sketch that it has already been converted to an array, because you want to make sure you're adding an array, not an image. Then the same thing for the loaded photo. After it's been converted to an array, then you want to take your photos array and use the append function to append the loaded photo. Okay, great. Then currently what we have are our sketches array and photos array as Python list types. So they're just a list, but we want to convert them to what is known as a NumPy array. The NumPy library is very commonly used with machine learning because it allows you to access a whole range of more complicated and nuanced functions for lists and arrays. So we want to convert our arrays here into NumPy arrays instead. So after the for loop, after all the images have been converted to arrays, we are going to take our sketches array and we're going to assign it to equal numpy.array out of the sketches array. So we're using numpy to create a numpy array type. It's just a regular list, but it's just wrapped in the numpy array type, which allows it to access more functions. Now, if we want to actually use numpy, we do have to import it. So make sure you import numpy. You have to import that library, and because we're in Google Colab, it is pre-installed already. Okay, next we have to do the exact same for our photos array. We have to take the photos array and use numpy.array to convert the photos array into the numpy list type. Array and list are synonymous here. All right, next up, to continue the processing phase, we are going to make sure that the value types are float 32s. So what I will do is I'm going to take my sketches, we'll start with that, sketches array, and we'll make sure it has the type of float 32, and then we'll reassign sketches array like that. And we'll do the same for our photos array. We're going to take the photos array and make sure it is of the type float 32, so all the values will be floats. This will allow us to have decimals. All right, and then we want to normalize our data. So this is going to be our last step of processing. We need to normalize our values. This is very commonly done in machine learning, though not always. And it is going to ensure that all of the values in the array are brought to the same range. That way, they'll all have equal value and weight. Okay, so for that, let's start with our sketch image here. We are going to take our sketches array and we are going to first convert it to the numpy float 32. So we'll take sketches array and we'll use as type numpy.float32. And then we're going to subtract the max 127.5 and divide by the max, 127.5. So that is how we normalize, the formula for normalization. You're going to take the max minus the min, which is just 0, so we take the max, and then divide by that max. And then we want to do the exact same for our photos array. So we're going to take photos array, and we are going to take photos array, and as the type numpy.float32, then we are going to subtract 127.5, and after that divide by 127.5. All right, and that is how you can normalize your data. We can run this code cell to verify that everything works. You should have the code cell run cleanly without any errors. And this is our code cell of data processing. Awesome. Okay, now that we have finished this phase, just give it a moment to run because it does have to load in all of the sketches and the photos, so it can take a little bit to load. Don't worry about that. You can also print out every index or print out every photo path to see progress as it's loading, because otherwise you won't see any progress. It'll just be running like this. But now that we have finished the processing phase, we can move on to our next section where we will actually start putting together our neural networks. So join me in the next section where we're going to start building our generator neural network. Hello everyone, and welcome back to our course. The next step of building our project is to build the neural network. But before we build it, we have to know what we are actually building. So we're going to dedicate a section to the fundamentals and understanding the theory behind the neural network that we're creating, the model, the algorithm. Starting off with, what is a generative neural network? This is the type of neural network that we're going to be creating, which can draw images. It can generate content, hence the name generative. All right, let's dive right in and let's talk about what this kind of neural network can generate. Well, there's actually quite a few uses to a generative neural network, not just our project of generating hand-drawn images and sketches, but actually these types of neural networks are used in many kinds of projects. For example, samples for image data sets, photos of faces. So yes, this neural network can generate not just drawings, but also photographs, as well as 3D objects. And in face aging applications, a generative neural network is what's used to do the photo alteration and to create that face aging effect. And as well, this type of neural network is used in photo editing and to create cartoon characters, to convert photos to emojis, and to create realistic photos. So you can use an algorithm to create content, and that content is relatively realistic looking depending on what the neural network is trying to create. How does this type of neural network function? Well, this neural network is actually two neural networks working together. So we have two models. The generative neural network has a generator as well as a discriminator, which we'll build later on. First, we have to build the generator. These two models are trained simultaneously in opposite processes. So they work together, these two neural networks that we'll create. There is the generator that we'll start with, and this is the neural network that creates the images. It tries to make as realistic looking images as possible. If you're creating images, you can also create other content. Then you have the discriminator. This is the second neural network that we'll build, and we'll dive more into it when we get there. But this model is part of this process as well, and the role of this neural network is to discriminate real images, meaning images that were actually created in a data set or that were created by a user, such as actual people who drew the images or took the photos, versus fake images, which are fake because they're generated by the generator. They were created by this neural network. They weren't actually collected. So however you want to discriminate real versus fake, that is what the role of the second neural network, the discriminator neural network, that is what its role is. So you have these two neural networks, the generator and the discriminator, and we're going to see how they work together to create this process of creating realistic images. Images that can fool a discriminator, which is trying to look for the fakes. So you have a generator, which is going to create images such as, for example, hand-drawn digits or hand-drawn faces. And then you have the discriminator, which gets real images, so actual hand-drawn faces, and it also gets fake images, meaning they were created by the neural network, the generator. And then these two work together. So what is the learning process? Well, the generator's learning process is to become better at creating images. The generator, you'll see, it will begin by creating just noise, just a bunch of pixels that don't have anything unique to them, that don't have any kind of shape. And then with each training loop that the neural network takes, with each machine learning loop, it's going to become better and better at creating images. So it's going to take its random noisy image and it's going to eventually create a realistic looking face if you're working with a face. Then what's the learning process of the discriminator, the second half of this neural network pair? Well, the discriminator, during its machine learning phase, during its training, it becomes better at telling apart images. It becomes better at finding the fakes from the reals, so discriminating between the two. And we're going to dive much deeper into the discriminator later on once we get there. So here we have the generator. It starts with noise, then it starts to change that noise into something that looks like a face by learning from your training data set. And at the end, the generator will be able to create its own unique drawings that it has learned to draw. If it learns to draw a face, it will draw a face. If it learns to draw a dog, it will draw a dog. If it learns to create a photograph or an artistic painting, it will do that, whatever you're trying to generate. The discriminator, on the other hand, that's the other neural network. And as it learns, first, it is going to start off by being probably quite wrong in its discrimination of trying to distinguish what's a real versus what's a fake. But it's going to get labeled data. This is a real image versus this is a fake image. And it's going to learn as it trains on that data set. It's going to learn how it can sort images into these bins of a fake image versus a real image until eventually, by the end of its training, the neural network is going to be good at discriminating if an image is fake or real. You have to find this equilibrium between the two neural networks because we have to reach equilibrium when the discriminator can no longer distinguish real images from fake images. Because at that point, you know that your generator is really good. If your generator is fooling your discriminator, then that means your generator is creating fake images that are real looking. Now, this does mean your discriminator has to be good, because if your discriminator is bad, well then it's not going to give you an accurate equilibrium. So you have to also build a stable discriminator that you trust to distinguish real images from fake images with some accuracy. And once you can fool the discriminator with your generator, well, that's how you know my generator is doing a great job. And here we see our generator is going to, by the end of the training, it's going to generate a whole bunch of face images, and the discriminator will think that they're all real, almost all real, however high of an accuracy you can get. And that's because the generator has become so good at drawing faces that the discriminator is now fooled. And that's when you've built a good generator. And that is an overview of what is a generative neural network. We're going to do a bit more theory about the neural network before we actually code it. And the reason is we're going to talk about the structure of this neural network. What is the algorithm behind the neural network? What are the layers of the machine learning model? So let's dive more into that coming up in the next lecture. Hello everyone, and welcome back to our course. In this lecture, we are going to talk about what is a convolutional neural network. Previously, we learned what is a generative neural network, and a generative neural network is actually a specific type of convolutional neural network. So now we're going to dive more into the structure of this neural network and how we can create it, starting off with what is a convolutional neural network. All right, so there are several types of neural networks. Let's talk about the big main types of neural networks. There is a feed-forward neural network, which is the most basic one, where connections are only going in one direction in the network layers. Then you have a recurrent neural network. This is a type of neural network that feeds outputs back into its own inputs, so it sends information forward and back. And this is commonly used for sequential data, meaning typically working with language data or textual data, you will use a recurrent neural network. And then finally, we come to a convolutional neural network, a CNN. And this is what we're going to be building in our project. A generative neural network is one type of convolutional neural network. So we need to break down what is a convolutional neural network. This type of algorithm machine learning model is commonly used with image data because it's perfect for grid topology data, any type of data that can be represented as a grid that has to take adjacency into account, which means each pixel is not just its own color value, but also it's relative to the other pixels. And that is how you can represent an image as data. For example, convolutional neural networks are used in computer vision. So they're commonly used with images or videos or anything where you have this type of grid topology. You have, for example, a two-dimensional image with width by height and then an even third dimension of color as well. And so you can use a convolutional neural network to find what is inside of an image by getting all of its pixels and then finding edges in the image. So you can outline an eye by finding the edges of the eye. If you teach your neural network what an eye looks like in terms of pixels and their relation to each other. All right, let's break down a convolutional neural network. It's a type of deep learning algorithm, meaning it's a neural network, and it's very commonly used to classify images. For example, to classify this is a dog, this is a cat, or to find eyes, noses, and ears inside of an image, as well as videos. Let's consider, think about a 500 pixel by 500 pixel red, green, and blue image, meaning a colored image. Let's say we have a 2-layer neural network with 100 units in the hidden layer. What do you think would happen when you flattened the image, this 500 pixel by 500 pixel image? What would happen when you flattened it in order to feed it to the neural network? Well, the result of flattening the image results in 750,000 elements because you have 500 the width, 500 the height, and then 3, which is the color values, red, green, and blue, to represent a color. So you end up with a lot of elements to represent your image. You end up with 750,000 elements of data to just represent one small image. And this is a lot of data because if you consider having 100 weights as well per element, then you end up with 75 million weights because you have 100 units by 750,000 elements. And that is way too much data. So working with image data is something that you have to take into consideration because even a small image of 500 by 500 pixels is a lot of data. So how do we handle this problem? What kind of problem would this cause? Because what happens when you have such a huge number of weights that are required in a neural network? How do you handle these large images or even just small images with a lot of data, as we saw? Let's first talk about what the problem is. The problem is that working with images, it's very easy to get into overfitting because you have so much data. A large parameter space is required to store a large number of training images. And as well, this can also lead to high computation costs. If you have images that have, even a small image can have a lot of data to represent it. So with machine learning, we need to handle the problem. We have to handle the problem of how do we work with images if they are containing so much data? Well, this is where we go into local spatial invariance. It's a fancy term, but we'll break it down. This means that anything detectable in one small region of the image, in one portion, will look the same if it appears in another portion of the image. And more on this, local spatial invariance means that the adjacency of pixels matters. Because when we're working with images, each pixel is not just an individual number. You have to take into account the pixels around it. If you want to find an eye or a dog, if you want to find the edges of a nose, you have to take into account adjacency of pixels. an image is not just a simple vector of pixel values. It has to take into consideration the neighbors of each pixel. Now, convolutional neural networks are used to handle the problem and the struggles of working with images because they're designed for grid topology. They're very good for working with images, such as classification or finding objects inside of images. Now, that is a convolutional neural network. This is the type of neural network that will help us work with images. It will allow us to work with images. And the generative neural network, which we discussed in the previous lecture, that is just a subset of the convolutional neural network. So next up, we're going to dive deep into a convolutional neural network, and we'll talk about the typical structure of this type of neural network for working with images. After that, we're going to go into each layer that we are going to build for our... Hello everyone, and welcome back to our course. In the previous lecture, you learned what is a convolutional neural network. You learned that this neural network is extremely good at working with image data, which is exactly what we're going to be doing. We're going to be creating images with one type of convolutional neural network known as a generative neural network. In this lecture, we're going to talk about how to build a convolutional neural network. What are the layers of a typical convolutional neural network? Then after that, we're going to dive into specifically each layer that we're going to build. But first, starting off, let's talk about the three main layers of a convolutional neural network. First, you have the convolutional layer, which gives the network its name. Then you have a pooling layer and a fully connected layer. Now, this is a typical convolutional neural network. So first, we're going to do an overview of what this type of neural network looks like typically, and then we'll jump into the specific layers that we're going to have in our neural network, which is specifically going to be for creating images, the generator. All right, let's talk about the convolutional layer first. A convolutional layer in a neural network extracts features from your source image. So this is part of the feature learning process. We talked about in the previous lecture how images are huge. They have so much data. Even a small image takes a lot of elements in order to represent it because you have to do each pixel in the width and height, and then also you have to do each color value if your image has colors. And so feature learning is a way to take all that data in one image and to make it smaller, so reduce the amount of data by extracting only the key features from the image. And this is going to be extremely useful because you will greatly reduce the amount of data required to represent an image. And that's very important because neural networks, they're already going to take a long time to train. So if you have a lot of input data alongside of that, then that would be even longer to train, and it would cause a whole range of issues, as we saw, overfitting, as well as computation costs. So feature learning is extremely important, and that's why we have the convolutional layer. Let's break down the convolutional layer. It's going to extract low-level features first from your image. These are edges or colors or a gradient. It's going to find those low-level features first. And the subsequent convolutional layers, so you'll typically have more than one convolutional layer in your network. These are going to build more complex high-level features, such as finding a nose or a face or eyes inside of the image. And these layers of convolutional layers, so these multiple convolutional layers, they're working together to extract the key features in any image you give it. Then after that, you'll commonly have a pooling layer as well in your traditional convolutional neural network. The pooling layer will downsample each feature, and this helps us reduce the number of features we have, feature dimensionality. It's going to reduce the data that is required to represent an image. And it does that by focusing on only the most important elements of an image. So pooling, it overall reduces the spatial size of co-evolved features, which means it's going to take the result of the convolutional layers and it's going to reduce the features even more. So it's all about reducing that image data because images are so huge and we have to address that problem whenever we work with images. Pooling will summarize a set of adjacent values from the preceding layer with a single value. This means it's going to take multiple features, so adjacent values, from the previous layer, the convolutional layer, and it's going to make a summary of it. So it's going to take multiple values and make them into one, which is how it reduces the data required to represent an image. The pooling layer is very similar to a convolutional layer because it's all part of that feature learning and feature reduction. But the key difference is that the pooling layer, if you have one, its operation is fixed rather than learned. And a pooling layer is not required, but it's important to know that it's an option. All right, next up, we have the fully connected layer. So this is the layer after the pooling layer, if you have one, and it's for classification. It will flatten the features of your previous layers into a vector. And that's because it has to produce an output that is a vector in order for us to have some classification result if we're working with a classification problem. The fully connected layer will connect every unit in one layer to every unit in another layer. So it's going to be near the end of your layers. And its goal is to learn nonlinear combinations of high-level features like the eyes, the nose, or the face. That way it can produce what it finds. The fully connected layer also not required. Of course, all of the structures of neural networks that you build, they can slightly vary. It depends on the project, depends on how you change your layer structures for the task you're trying to achieve. So a fully connected layer you may or may not have, depending on what you create for your structure and what you've researched for the typical best structure for your specific project. If you don't want a fully connected layer, you could just stack convolutional layers as so long as you output the correct number of classes. Your output has to be the proper shape, but you could just have your last layer be the convolutional layer. But the fully connected layer, where it exists, it will predict the probability that an image belongs to one of several possible labels if you're working on a classification problem, which is very commonly done with a convolutional neural network to classify what is in this image. So in this example, we have an array here, and it contains 10 different elements from 0 to 9. This means we have 10 classes that the image could possibly belong to, and this could be anything. This could be numbers 0 to 9. This could be dog, cat, bird, plane, turtle. Any 10 different classes that we're trying to classify our image into. And the result of this neural network is going to be the probability that the image belongs to a certain class. Typically, one will have the highest probability, such as if the image is a cat, then the element that represents the cat will have the highest probability score. Of course, that's assuming that your neural network learned correctly. So overall, the convolutional neural network, it will take an input image. It will then assign importance to different aspects or different objects of the image. And it does this with learnable weights and biases, so with machine learning algorithms. And that's how it can detect what is inside of an image or what is an image. And as such, it's highly attuned, highly formed and structured to differentiate images from each other. A convolutional neural network has spatially local connections, as well as patterns of weights that replicate across the units in each layer. So there's a lot that you could learn about it if you want to research more into its specific structure, and if you want to build one completely from scratch without using any helper libraries like TensorFlow or Keras. But we will be using TensorFlow and Keras to help us build the layers. It saves a lot of time. As well, a convolutional neural network will have what's known as a kernel or a filter. You'll see this more later on in this very section. And a kernel or a filter, this is a pattern of weights, and it's replicated across multiple local regions of the image. It's a window, and you don't look at the whole image at once. You look at a tiny portion of the image, and then you go throughout the whole image in that tiny window. So you go through each image one little section at a time. So how do we achieve local spatial invariance, which we talked about near the beginning of this very lecture? Well, in order to achieve that, you are going to constrain weights connecting a local region to a unit in the hidden layer to be the same for each hidden layer. And that way, you can get the different associations and neighbors of pixels. The kernel that we talked about is going to make hidden units into feature detectors that can detect the same feature wherever it appears in the image. So if you see, for example, one common edge pattern in the top left-hand corner of the image, you can recognize it again in the bottom right-hand corner of the image. Now let's talk about what is the convolution part of the convolutional neural network. Well, it does refer to that convolutional layer, which itself is when you apply a kernel to an image's pixels or to the spatially organized units in a subsequent layer. So the convolution part of the name of the network, it's referring to that feature reduction and that reducing of data that's required to represent an image. There are some issues with convolution that we have to handle. For example, pixels on the edges of an image are used in fewer outputs compared to pixels in the middle of an image. And this might not be something that you intuitively grasp immediately, but as you look more into convolutional neural networks and build them, you will see that this is the case. And so how do we handle this issue? Because this is going to cause your image size to shrink, and you don't want that to happen. Even though you are reducing your image dimensionality and the number of features you have that you need to represent an image, you don't want to actually shrink the image size itself, because you could lose valuable data if you do that. So how do we address that issue? Well, what you do is you apply padding to add zeros to image borders. So you take the image and you add padding to it, so that way when you start your convolution of the image, you don't start from the very edge, you actually start on some padding that is okay to be cut off. And we're going to see that later on when we need to apply padding inside of our neural network layers. You'll see that come up. Convolutional layers have very few parameters. Most are in the fully connected layers, and pooling layers have no parameters at all. The image size reduces gradually as you go deeper in the network. So you start with an image, it could be 500 by 500 pixels or 28 by 28 pixels, and you are going to reduce it gradually as you go and convolute it, as you perform convolution on it. Now you're still keeping the important features, so you're not actually going to reduce the important features, that's why we added padding, but the image size will reduce as you go deeper in the neural network, and you'll see that when we actually build out all the layers. You do have to be careful though. If you reduce the image size too fast, then you will have worse performance, because then you could lose valuable data. If you take a 500 by 500 pixel image and you reduce it to 5 by 5 pixels, well, then it's very easy to lose important features of the image if you do it like that. So you do have to be careful with how quickly you reduce features. You have to do it one step at a time, that feature reduction. Now, there has been a lot of research done on how to put together different layers to build effective convolutional neural networks. I'm going to be showing you one structure of a convolutional neural network when we build it together for our generator, and then later on as well for our discriminator. And these are structures that have been tested, and so there has been research done on that. It's an effective way to put together the different layers. But of course, because machine learning is still a relatively new field, there's a lot more that can be done, a lot more research you can do, and a lot more innovation to be done, even with convolutional neural networks. So even though there are some structures for neural networks that are trusted, that you can use to start your projects, and you can expect them to perform well for the project that you're trying to do if it has been done before and researched, there is still the opportunity to use a different structure. So you can put together your own structures of layers and test out if those perform better. And that is how you can build a convolutional neural network. In the next lecture, we're going to start going deep into every single layer that we're actually going to build for our generator. So before we code it out, I want you to understand what each layer actually is doing. So we're going to go step by step, layer by layer, through our neural network specifically. So now that we know in general what this type of neural network looks like, we're going to go specifically through each layer in the one that we're going to build that is going to be for drawing sketches. So join me in the next lecture where we will start by looking at the layers of our generative neural network. Hello everyone and welcome back to our course. In this lecture, we're going to do an overview of the layers of our generator. And then in the next section, we're actually going to code out all of these layers. So let's look at these 4 different layers. We're going to have a 2D convolution layer, transposed convolution layer, batch normalization layer, and a ReLU activation layer. And we will have several repeats of convolution so that we can convolute incrementally over time. Starting with convolution, let's talk about what is 2D convolution in the first place. This is a convolutional layer of your neural network that can extract features from a source image. And it does this by taking some image and applying a kernel to it to produce an output. And the output is a smaller representation of the image. The kernel will start at the upper left-hand corner of the image, and it will perform element-wise multiplication. And in this way, it's going to produce a scalar output, which means a single number for that overlapping area. So it can reduce the features in an image greatly. As well, then the 2D convolution layer will move 1 step over if stride is 1, 2 steps over if you set stride to 2, etc. And it's going to repeat its convolution process across the entire image. It's going to go with that window. Now, generative adversarial networks, which we're building a generator. These generate a small matrix, and they do this by using a convolution to upsample that matrix then to the true image. So that is how it can create a new image. It first generates the matrix, and then it uses that to upsample that matrix or that smaller representation back into the original image size. But of course now it's going to be the generator's fake image instead of the real image. And inside of the network, weights will allow for upsampling random noise to the actual image. We are also going to have another layer known as transposed convolution. This is very similar to 2D convolution, so we're going to have both types of layers. But with a transposed convolution, instead of downsampling an image or making it a smaller representation with fewer features, transposed convolution does the opposite. It does that upsampling. It will take that matrix and it will upsample an image back to its regular number of features. And that is going to upsample the image back to its regular size, and it's also going to create the new fake image in the meantime. It's not just bringing back the original image. It's going to make the images larger, but it's still going to be a fake image. It's not going to be that real image. So transposed convolution, it takes the output and it is going to create the original image size with that kernel that it created. Here is an example of some code that creates a convolutional 2D layer. We're going to see this in the next section where we actually build out the generator. So here we're using the Keras layers module, which has the framework for a conv2D object. And we just have to pass in several parameters here: filters, kernel size, strides, and padding. So let's talk about all of those different arguments, starting with the filters. This refers to the number of output filters of the network. Then we have kernel size. This refers to the height and width of the 2-dimensional convolution window. And if you only have one value, then it means you're working with a square convolution window. Then we have strides. This refers to the stride of the convolution along the height and width, so how much you're moving over each time. And finally, we have a padding algorithm, which can either be the valid padding algorithm or the same padding algorithm. These are 2 options for you. Now, conv2D transposed or transpose, this works very similar to conv2D. In terms of the creation, you just call a different layer type, but you still use very similar arguments. And this time we are upsampling the image. So that is convolution in our 2 convolution layers. Next, let's talk about another layer type that we will have in our generator neural network, and that is batch normalization. So we come to a problem, and that is that training networks with a lot of hidden layers is hard. And you will see that our generator is going to have a lot of hidden layers. The reason that training networks with so many layers, so much convolution mostly, is hard is because all of the layers will change during an update. We need to have many convolution layers in order to iteratively downsample and then upsample the image. We can't just downsample and upsample in 2 big steps, because then we'll lose valuable features. We have to downsample and then upsample incrementally. But because we're going to have so much convolution, this is going to make training hard because all of our layers must change during an update. And therefore, the update process will chase a moving target, because your machine learning model is going to learn and it's going to update, but then it's going to need to update again every time all the other layers change. They all affect each other, and so you're chasing a moving target. So where do you stop? Well, that is the problem. As the parameters of previous layers change, the distribution of each layer's inputs will change during training. So there's a lot of moving targets and also this distribution that's going to change. So our solution is to use what's known as batch normalization, and this is going to be a layer that you typically will include after every convolution. So batch normalization. This layer will scale the output of each layer, similar to how we have done normalization before on images. We're doing normalization again, but this time on a batch. So at every batch, we're going to normalize the activations of the previous layer. And this is going to standardize the inputs of our network, because now all of our values will be on the same scale. And that is that next layer, batch normalization. Next, let's talk about another layer we'll have when we start coding this generator, and that is going to be the ReLU activation function. So what is an activation function? Well, an activation function takes a summed weighted input from a node. So it takes an input and it produces one of 2 things, either an activation, so it will activate the node at the neuron, or it will produce an output. We are going to use a specific type of activation function to perform this task, known as rectified linear activation, ReLU. And this is very commonly used with neural networks. There are other types of activation functions as well, many other types, but this one is commonly used for neural networks and for generators. But of course, you could change around your structure and experiment with using different activation functions as well. This activation function is the recommended activation function for neural networks. Here is a visualization of the activation function. So what it's going to do is return X, the input, or 0 if the input goes below 0. And that is how it affects the activation of a node. So where X is the node's output, the activation function will take that output and it will activate it. And if you're interested in visualizing this activation function, you can use this code in Google Colab or just anywhere in Python, and you will get this visualization of it. So what is this activation function? Why are we using it? Well, it's very popular for neural networks because you can train deep supervised neural networks without unsupervised training. So we only need supervised neural networks. And it's going to prove very useful as our activation function of choice, because we need activation functions to activate every single node. And ReLU is very commonly used for neural networks. And those are going to be the layers of our generator. Coming up, we're going to put them all together, and you'll see we're going to have quite a few hidden layers. We're going to have many different convolution steps, and we're going to have convolution followed by normalization followed by activation, and we're going to do that iteratively to downsample and then upsample our images. All right, so join me in our next section where we're going to put all our theory into practical application, and we are going to build our neural network.
Hey everyone, thanks for watching this course. If you want to watch the rest of the course, the link is down below. Not only will you get the access to this course, but you'll get access to a lot of other courses in a huge bundle, and it's on sale today. So buy before the sale ends. Thanks for watching, and I'll see you in another video.